everyone, Screen913 here. How's it going? Welcome to another edition of Thoughts Behind the Wheel, Astronomy edition. I had a lot of people really enjoy the a little astronomy edition we had last time, and I had a lot of people ask questions, and a lot of people asked me to go into more detail, and I am happy to oblige, actually. If nothing else, it'll help me review for the test, I guess. I got a final coming up, so woo! Yay! Finals! Woo! Finals! Woo! And it just so happens I have a rather long drive today, because I have to drive all the way across the Metroplex to go to an outlet mall to pick up stuff for my journey to the southern of Korea. Which is like an hour there and an hour back. So I have plenty of time. However, since I am driving at the moment and I can't really read the questions that were asked of me, and there's no way in the world I would remember them all, I had to come up with an ingenious way to do that. And the way I did figure out how to do that was to take a voice recorder and actually read the questions so that I could play back the voice recorder. Huh? Yeah. All right. Look at that. So that's using the old noggin, I think. I like to think that's using the old noggin. Could just be okay. Hang on a second. Traffic is slowing down. I don't know why. Oh well. Okay, there it goes. I guess people just stopped for a second because they wanted to enjoy the Texas heat. I don't know. In any case, so my thinking is that I just kind of go down the questions one by one and answer them in detail. Okay? Now, again, if you're not a big fan of astronomy or don't really care, then, probably shouldn't listen to this and just, go watch something else. Alright. So, first question is...
Okay. In 7 Firebird asks, Farscape, a combination of radiation wave and a black hole sent a manned ship to the
Oh, yes. Okay. In 7 Firebird, I'm not going to get all your names right, but in 7 Firebird, I think, asked, basically he was talking about Farscape, how a black hole, a mix of black hole and radiation, which black holes constantly exude radiation, so, well, actually, they don't exude radiation. Radiation does come from around a black hole, but the black hole itself doesn't exude radiation, because radiation is just a form of light, and, well, light can't escape. But anyway, the question is, in Farscape, a black hole basically sent him all the way across the galaxy, and is that possible? And the answer is, yeah, maybe. Probably not, but maybe. The simple truth is we don't know. It is theoretically possible. Because, and I have to explain why. Imagine the space we live in as a fabric. And in fact, people call that all the time. I'm sure you've heard it called space-time fabric. Imagine it's a giant sheet. We're all sitting on top of a giant sheet. It doesn't really work this way, but it'll help you visualize it if you visualize it this way. We are sitting on a sheet, and our planet's on a sheet, our sun's on a sheet, everything in the galaxy is on this sheet. And the bigger the object, the more gravity it has, the heavier it is, and therefore the further down it drags the sheet. So in other words, if you have a flat sheet just suspended in air, and then you put a bowling ball on it, obviously it's going to pull the sheet down, and there's going to be an area of the sheet that's pulled down by the sheet. And things in this, and basically, if you think about it, oh gosh, it's so hard to say this without a visual demonstration. But let's say I have a flat sheet, and I put a bowling ball on it. That bowling ball is going to drag the sheet down, which means that the corners of the sheet are actually going to become closer together. You see what I'm saying? Like, it's going to take, if you take 2 points of a sheet, then let's say they're 3 feet apart from each other, and then you put a bowling ball in the middle, okay, sorry, I got a call. So basically, what gravity does is gravity bends the space-time fabric around itself, which means it can literally draw 2 points of space closer together. And a black hole theoretically would do this. Why? Because a black hole is a massive well of gravity. This is basically how warp drive technology works in Star Trek, more or less. What the warp drive technology does in Star Trek is it basically, I'm guessing through gravity, I don't know the details or the specs, but I'm guessing through gravity, it actually creates like a gravity well or something that actually pulls 2 points of the galaxy closer together and then travels between those now closer points. It's not like in Star Trek they're actually moving faster than the speed of light, they're just warping, thus warp technology, time and space around them so that the points they're trying to travel to are actually closer together. And this technology is theoretically possible. And therefore, it is theoretically possible that if a black hole was big enough and massive enough and had enough density to it, that the gravity could be so great that it would pull the 2 points of space-time closer together, thus allowing whatever his face name is to actually be shot to the other side of the galaxy. Theoretically, it is possible. I'm not saying that yes, the answer is right. I'm just saying that we have not found any substantial evidence one way or the other. But that we have some belief that yes, maybe this could happen. Probably not the answer you were looking for, but you know, it's the closest you can get when it comes to theoretical physics. Alright, next one.
Now I know it's fiction, but this way, do you think there's any plausibility behind it?
Yeah. Waiting for myself.
Chaotic idealism has two astronomy questions. One, why isn't Pluto a planet anymore? And two, how do solar systems form in the first place?
Alright, Chaotic Idealism asks, one, why isn't Pluto a planet anymore? Good question. Pluto is actually called, and actually there's another question here that asks what a dwarf planet is, and this is what Pluto is. Pluto is a dwarf planet. Alright, the reason why Pluto is no longer the 9th planet was because we kept finding objects in the solar system that were as big, or one that was even bigger than Pluto. And we had to ask ourselves, if we have objects that are just as big as Pluto, or even bigger than Pluto, should they also be planets? And what technically defines a planet? Because as crazy as this sounds, we had never really defined what a planet is. I mean, we just kind of accepted it for, you know, it's a planet. It's a planet. It's big and circular. It's a planet. But we never had a solid definition for, yes, this is a planet, no, this isn't. Until, I believe, 2006, when this whole question thing came up. Because we'd never really needed to define it before. However, like I said, we found, I'm trying so hard to remember the name. I think it's Iris, like E-R-I-S, I think. I don't know, don't quote me on that, but I think that's the name of another object floating in our solar system that is actually bigger than Pluto. And there was another object that's as big as Pluto actually floating around in our asteroid belt. And, like I said, it begged the question of, okay, if we keep finding these sort of objects, do we make them planets? Or does this mean that Pluto is no longer a planet? And what they decided was that instead of continuously adding planets to our solar system, it would be more accurate to actually define Pluto and these other planets as a dwarf planet, not a real solid planet. And the definition for a planet now, that we have one, is twofold. A, it is big enough in mass that the gravity pull outweighs the structural integrity. In other words, it gets formed into a sphere. Why? Because gravity is so great that everything is pulled into a spheric shape. You know, if you look at asteroids are all kinds of crazy shapes and weird rock-like shapes because the gravity of that asteroid isn't strong enough to pull it all together into a sphere. So a planet A has to be big enough and massive enough that the gravity can do this. The gravity can overcome whatever structure it was originally and pull it into a sphere shape, which Pluto does do, but Pluto doesn't match the second criteria, which is the second criteria of a planet is that it is also massive enough to clear out its orbit from neighbors. In other words, the gravity is so big that it either kicks out everything in its orbit or pulls it into a satellite orbit. In other words, a moon. The gravity of all of our planets, all 8 planets in the solar system, is so great that the area it's traveling, its orbit around the sun, it either kicks anything in this orbit out of the orbit, or it pulls it in to become a moon, or it pulls it into the planet and it explodes. But one of those two things. Pluto is not big enough to do this. Pluto can collapse into a sphere, but it's not big enough to actually clear out its orbit. And therefore, it's not really a planet. It's kind of in between. It's what we call a dwarf planet. And I think there are like 6 dwarf planets in our solar system. The one I told you, Eris, that was actually like bigger than him. I think that's his name. And there's another one like starts with the C, but I really can't remember. That's actually in our asteroid belt. All of these fit that term. They are big enough to collapse into a sphere, but not big enough to clear out their orbit from other bodies. And that is why Pluto is no longer our 9th planet. Poor Pluto. Actually, poor Pluto. What are you talking about? Pluto was living with the kings when it shouldn't have been. Damn infiltrator! Pretender! I say we burn it at the stake. As soon as we find a stake big enough to burn it on. Yeah, so that's that question. And the next question was, how do solar systems form in the first place? And that is an interesting question. It depends on how in-depth you want me to go. Okay, let me give a brief overview, and then I'll get more detailed as I go along as it becomes more pertinent. The universe was created. Boom! Big explosion, the Big Bang. You may have heard of it. And this big explosion thingy created our first generation of stars. And we theorized that when the universe was first made, the first thing that there were stars and gas, like nebula gases and giant stars. Because really the only thing that formed at that time was mostly hydrogen, which is the most abundant element in the universe and easiest to make and easiest to manipulate, etc., etc. And they formed these giant stars, these like superstars. And these superstars, hang on, where am I going? Oh no! Oh no! I think didn't go far enough. Curses. Oh well. Anyway, they formed these superstars, and these superstars didn't live very long. For the comparative lifespan of a star, that is. Because they were giant stars, and giant stars burn through their fuel very quickly and they explode. However, in these stars, in the core of these stars, it was hot enough and dense enough to create heavier elements like neon, magnesium, oxygen, carbon, and eventually iron. And when these stars went supernova, the supernova was hot enough to actually create even heavier elements than that. California, Berkeley, all the other heavy elements. And these supernovas threw out all these heavy elements into the universe. They just and these heavy elements mixed with gas formed new nebula. And these new nebula eventually formed new stars. Well, and these stars would form at the center of the nebula cloud. And it would suck in all the gas, all the hydrogen, and all that stuff, and it would start burning into a star. Well, now you have all these heavier elements around there too, a lot of which the sun didn't actually suck up. And these heavier elements, rocks and stuff, would still orbit the sun. And by the nature of gravity, they would orbit the sun, and they would also begin to cluster together because they would be pulling on each other. And these other elements, and whatever leftover gas there was, would start pulling together into these miniature spheroids, which would be like the planets. And we theorized that at the beginning of our solar system it was very chaotic. There were tons of small rocks everywhere, and the new planets were getting bombarded constantly, thousands and thousands of times, adding to their mass, tearing some mass off, adding more mass, collapsing together. It was very, you would not want to have a summer home there without some sort of insurance. That's what I'm trying to get at. And what would happen is these rocks and gases and stuff would eventually coalesce while orbiting the sun into planets. Yeah. Yeah, and then these planets would continue their orbit, and they would eventually maybe have some satellites around them, which would be like the moons and stuff. and you would have, like, generally speaking, you have rock planets closer to the sun, and gas planets or gas giants are further away from the sun. Now, the reason why the gas giants are further away from the sun, there's several reasons for that. Some of it's solar winds blowing them away. Other parts of it is because they have more mass, they're bigger, and thus, because they have bigger mass, they have higher orbits because they have more speed and gravity pull of their own. And are actually, yeah, anyway, there's a whole big reason for why certain planets are where they are. But anyway, that's generally how a solar system forms. Are we good? We good? And that's just a single-starred solar system. A lot of the solar systems that we know of, or even the stars that we know of, are actually binary systems, which are two stars orbiting each other. And they probably have their own planets orbiting them, and it's going to be very complicated. So yeah, that was that question. Alright, Jake the Snake wants to know, what happens if a black hole eats something like a planet? Will it increase in size? That's kind of the paraphrase. Yeah, first of all, you have to understand that even eating a planet is like throwing a pebble into a pond. In order for a black hole to form under normal circumstances, the object needs to have 3 times the mass of our sun. Now, that means that it needs to have 3 times the mass of our sun when it collapses. And over the course of a star's life, it will lose over 80% of its mass to other stuff, to the explosions, to the Big Bangs, to the everything else. So what's left, that 20% or less that's left, has to be 3 times the mass of what our sun is currently. So it has to be a massive object to become a black hole. And our sun is huge. And if you throw a planet at our sun would swallow it up and not even blink. So if you take something 3 times the size of our sun and throw a planet at it, you know, it'll crush it and probably not even notice it was there. But the theory is still coherent. What happens if a black hole eats up more mass? Will it get bigger? Yes and no. If you talk about the black hole as a whole, meaning the event horizon and the singularity and everything, yes, theoretically it could get bigger as the mass gets bigger, the gravity's effect will become stronger, and therefore the event horizon will become bigger, because the more gravity pulls, the further away it can trap light. So yes, indeed, it will get bigger eventually if it eats up enough. Partially. However, the singularity inside will never increase in size because it's already been crushed to a volume of 0. And, you know, 0 doesn't, you can't, it's like a singularity, it's nothingness. It just crushes it into a singularity. It never gets bigger, it just gets more dense. How that's possible, we don't know. So while the singularity itself will never actually get bigger, the event horizon could feasibly get bigger. I don't think we've seen any proof of this. We may have. I mean, we've never seen it with our eyes. It's so hard to see black holes anyway. But the mathematics would state yes. As the more mass is introduced, the gravitational field should get stronger, therefore the event horizon should expand. But this would be a very slow process unless you throw something really enormous at it. And the simple truth is, remember, black holes don't suck up a whole lot. I mean, they don't have any more gravity than they did in the first place, which means that if the object wasn't already falling towards it, it won't start falling towards it now. So most black holes kind of just sit in their own little space, and they're not really sucking anything up. There's a few who happen to form, like, say, close to a star, and it's eating that star up. Or there's a few where a rogue planet may get blown into its orbit and sucked down. But for the most part, no, black holes are kind of just in their own little area that's already been cleared of everything. Just like, for example, if our sun went black hole for whatever reason, you know, there wouldn't be much for it to eat. Maybe a few asteroids or comets would go by once in a while, but our planets are too far away for it to suck in, so it would just kind of sit there, maintaining its size. But yes, the answer is yes, it can grow in size if enough mass is introduced to it. It's just probably rare that would ever happen.
It increases gravitational field.
Alright, hang on. Next one.
The Viking asked if it's possible to turn people into black holes.
Alright, so I didn't catch the name, but one of you guys asked if it's possible to turn people into black holes. Yeah, possible as in how? As in mathematically possible? Yes. Everything in the universe has a Schwarzschild limit, which means that if you were to take a human and crush them into a size of a certain diameter, eventually the density and gravitational pull of that diameter would become so massive that it would collapse everything into a black hole. So mathematically, yes, you could. Physically, we have no capability to do that whatsoever. I don't know anything that has the capability to do that whatsoever. So it's kind of like one of those, can you travel the speed of light? Well, sure, mathematically you could. Do we have the capability? Not a chance in hell. So, I hope that answers the question. Next is...
Neverwinter's Night asked if a meteor was caught in the sun's gravitational pull.
Yes. Neverwinter's Night asked if a meteor is caught in the gravitational pull of, say, a star, and it gets a boost of speed from somewhere, can it break the gravitational pull? I believe that's what the question was asking. And the answer is yes. Most certainly it can. Interesting thing about orbits that most people don't realize is that all an orbit is a free fall, but moving sideways at the same time. Imagine, if you will, our satellites that fly around the Earth, or even the Moon. Let's take the Moon. The Moon is constantly trying to fall towards Earth. I mean, literally, it is falling really fast right towards Earth. The problem is that it's also moving sideways. And it is moving sideways so fast that it keeps missing Earth. Imagine if I throw a ball. Yeah, here's a great example. Let's say I throw a ball at a post, a building. Let's say I throw a ball at a building. And I throw it at the building as hard as I can, but I'm also traveling in a car that's going parallel to the building at like 50 miles an hour. And what happens is I throw that ball at the building as hard as I can, but the car is going sideways so fast that the ball misses the building, because the ball is also going parallel to it at 50 miles an hour. And so it misses the building instead of hitting the building. Now imagine if this never stopped. If the ball kept trying to hit the building but was going sideways so fast that it kept missing the building and trying to hit the building and missing the building and trying to hit the building. That's what an orbit is. As crazy as that sounds, that's what it is. Every object that's in our orbit around our planet is trying its best to fall to our planet, but it's just going so fast it keeps missing. That is an orbit. Now, if you take less energy, in other words, you reduce the speed of that object, well, then it'll fall into the planet. If you increase the speed of the object, it'll move sideways faster than it is falling towards the planet, and therefore break the orbit or move to a higher orbit, meaning it gets further away and gets a wider circle. So that's basically, and there's a escape velocity equation. It's an equation that determines how much force you need to escape any size of mass. Once you hit this escape velocity, you are no longer in orbit of that mass. If you're below the escape velocity by varying degrees, you cannot escape the orbit of that planet. So in other words, a rocket who wants to go to the moon needs to exceed this escape velocity, or it will never leave the planet. So to answer your question, if a meteor is in orbit around the sun, okay? The sun is doing its best to pull in that meteor. The meteor is trying to fall to the sun, but it is also moving another direction so quickly that it never makes it, and so it enters a circular pattern. If it gets a boost of energy from whatever, let's say an asteroid collides into it, let's say it wakes up one day and decides it's Batman, and Batman has like way too much willpower, and so it has a massive energy now. What? You've never seen asteroids think they're Batman? Oh, it's quite hilarious, I assure you. So, it gets a boost of energy. Well, now it's going sideways faster than it was before. If this sideways speed is enough, it will break orbit and just fly off into the great beyond until, forever, or something else sucks it in. Something with more gravitational pull. Or, at the very least, it'll enter a higher orbit, meaning it doesn't have enough to reach escape velocity, but it's closer, and therefore it has a wider orbit. because it moves sideways faster than it's falling towards the sun. So I know, I kind of repeated myself quite a bit there, but I hope that answers the question.
Let's give it a boost of speed.
Next question is...
What would it burn into bed to make muffins? King asks...
Yes?
The king, I'm not really sure.
Get over the squeak!
Does a black hole gain mass by absorbing mass and thus get bigger? The second is what has to collapse in order to form a supermassive black hole?
Okay. Kang? Tehkng. I remember that name because I remember not knowing really how to pronounce it. Kang? I'm not sure. Anyway, first of all, he asked, does a black hole get more massive by eating objects? We already covered that question. But the other question he asked is a really good one. What has to collapse to form a supermassive black hole? And the truth is, we don't know. We have some theories, but we don't know. We don't have any idea what actually caused a supermassive black hole, because whatever caused a supermassive black hole had to be many times the size of anything else that we've seen of our normal star. It would have to be billions the size of our star to collapse into a supermassive black hole. And stars have a limit. Normal stars have a limit that they can reach. I forget the name of that limit. But generally speaking, there is a size that stars can reach, and after that certain size, the radius or what's it called? The surface area of the sun is so massive that it radiates the energy so quickly that all the fusion in the world will not let it get bigger. So there is a limit. There's like a hard limit to how big a sun can get. Now this is massive. This is a massive limit. But it's still not big enough to make a supermassive black hole. So something else had to be making them. And there are a few theories, but we don't know what they are. The one theory is that at the center of the galaxy there were these huge cluster of stars. And these huge cluster of stars somehow collided all into each other, and that was somehow enough to push it over the edge and create a supermassive black hole. There is a theory that maybe suns at the beginning of the universe were much bigger, but again, that runs into that problem I just said of the kind of limiting size. Now, we do know, or we have evidence to support, that there were supermassive black holes in the first billion years of the universe, which is astounding because we have no idea how that's possible. We don't know how anything got that big, that it could make that big of a black hole. It just did. Yeah. So the answer to your question is we don't know. Hopefully we'll find out one day, but it's one of the greatest mysteries right now. We know that supermassive black holes exist. We theorize that they are at the center of it is at the center of our galaxy, and that it's at the center of many galaxies. We have proof that there is one at the center of one galaxy, which is what leads us to believe all the other are also supermassive black holes. But we do not know exactly what has caused them. Alright, next question.
AK-15 asks, what could have made the black hole at the center of the galaxy?
Hey, he asks what could have made the black hole at the center of the galaxy. See last question? Hopefully I explained that one well enough. Next.
Sniper Joel asks, is it true that most stars you see are actually planets in the distance?
Yes. You know, now that I think about it, past squee. What the hell, dude? You were reading all these out one after another. If you read one question and then read another question that was exactly like the question before it, why the hell did you even put this on here? You and I are going to have words later. Honestly. What were you thinking? Okay, the next question is it true that most of the stars we see in the sky are actually planets? While I think most scientists would love this to be the case, no, not at all. The only planets you can see from the sky are, without the aid of telescopes and other cool stuff and devices like that, I believe Mercury, I'm not quite sure on Mercury, but Venus, Mars, Jupiter, Saturn, maybe Neptune. I think that's it. I think those are the only ones you can see with the unaided eye. And those are very, very close. The reason why you would not be able to see any other planets is because planets don't really generate their own light the way stars do. Stars are incredibly hot and they generate light in the form of heat and radiation. Planets don't do that. Planets only reflect the light that is bounced off of them by the sun. And therefore, what you see at the night sky when you look at a planet or even the moon, all you're really seeing is reflected light from the sun. And other planets, even though there are lots of other planets we have discovered, thousands and thousands of them, I actually have an application on my iPhone that shows every single planet we've ever found and where it is in accordance to the Milky Way galaxy. And almost all of them, if not all of them, are actually gas giants. Because that's generally the only way we have of detecting them right now. I believe we might have actually found an Earth-like planet, and like the scientific community is abuzz with it. But we found thousands of them, I think. At least hundreds. I'm pretty sure thousands. And like I said, I can pinpoint exactly where they all are. But we cannot see them. Definitely not in the night sky, and not even with like the Hubble Space Telescope. We have to know they're there through other methods. Basically, spectroscopy, which is a form of science where we analyze light waves. And light waves tell us all kinds of nifty things. Like what elements are in the sun, how hot the sun is, if there's something circling the sun, all kinds of stuff. Or we can look at gravity. For example, if a star is acting in a certain way, or some object is acting a certain way, as if some form of gravity is pulling on it, well, then we know maybe there's a planet there because something has to be pulling on it. So there's other ways we find it, but no. But you know how you can tell a planet from a star? A planet doesn't twinkle. You know that twinkle, twinkle, little star? All the stars in the sky twinkle, even a little bit, except for planets. Planets are just a steady, constant light. Why? Because they are too close for light to make the little twinkle thing. So, yeah. So, next question. Oh, that's it. That's all the questions. Okay. So what else? What else can we talk about? Here's an interesting idea. Have you guys ever wondered how we know these things? Have you ever, because I always did, I always thought it was fascinating. Like, you watch the Discovery Channel, and the Discovery Channel tells you, well, the sun is made up of helium, mostly, and a little bit of hydrogen, and some other trace elements. And you go, oh, that's neat! Do you ever stop and go, wait, how the hell do we know that? It's not like we can just go over there and scoop out a section of the sun and be like, oh yes, well here's the helium, here's the hydrogen, oh, right there's the hydrogen, lots of that. No, or they go, the sun is the actual photosphere of the sun is 5,000 degrees Kelvin, but the corona, jumps up to like 5 million Kelvin, and you're like, wow, that's awesome. Wait, how do we know that? Pretty sure my thermometer doesn't pick up that kind of temperature from that distance. And here's how we tell. A lot of it is done through what I said before, spectroscopy. I cannot say it. Don't sue me. I can't say the word. I don't really know how it's said. But it's the science of studying spectral lights. Light, I'm sure most of you heard, light acts as a wavelength and a particle depending on what state it is and what you're doing to it and how energized it is. The more energy it has in it, the more it acts like a wave. The less energy it has in it, the more it acts like a particle, with extenuating circumstances, yada, yada, yada. But anyway, if you analyze a wave of light, you will notice that this wave of light, once you get really close to the wave of light, has little, like a wave of light looks like, you've all seen a wave, like a sound wave or a light wave or a wave in the ocean. It's like an arc and then a dip and then an arc and then a dip, right? Well, these aren't perfect arcs and dips. They're not. If you look really closely at them, each arc has little dips and little spikes. And by analyzing what these are and what caused them, we can learn a whole lot. For example, emission lines, which are the spikes in each arc, are caused because when a particle gets energized, the electron bumps up. Okay, you know what? I have trouble quite understanding that one, and there's no way I'm going to be able to just explain it without a visual aid. But basically, the short end is when a atom gets energized because it was hit by something, the electrons in the atom like to jump up to another orbit, but they don't like to be in that orbit. So what they do, when it gets hit by a photon, it jumps up in orbit, and it then, as fast as it can, downgrades back down to a stable orbit. And in order to do that, it has to release a packet of energy. And that packet of energy that it releases is what we're picking up on the emission spectrums, the spikes. And then there's absorption spectrums. Absorption spectrums are the dips in the arcs of light. And what that's showing us is that when the light passed through a certain element or a certain element, that element absorbed a tiny piece of that light. So what we can do is we can look at the light from the sun using a special tool called the spectrometer. And that spectrometer will show us all these little dips. And by looking at these dips, we can tell what elements this light had to pass through in order to get to us. And by doing that, we're able to tell what kind of elements are in the sun. Isn't that kind of cool? And you can literally, I mean, they have charts that have, if you see these spectral lines, that's the element you're looking at. If you see these spectral lines, that's the element you're looking at. If you see these spectral lines, that's the element you're looking at. So you can identify all the elements in the sun by looking at the spectral lines. Or really all the elements of almost any object by looking at these spectral lines. It's just quite astounding, honestly. You can also tell if it's red shifting or blue shifting, which is the Doppler effect of light, and probably should go into that later on, at another time. But yeah. So, and temperature kind of works the same way, because we can look at the spectral lines, and the temperature will affect spectral lines differently. And by looking at the spectral lines themselves, we can say, oh, okay, well, there's certain things we can do. For example, we can say, okay, there's this element, and this element is charged, and we know this element doesn't get charged unless it hits this temperature. So we know it has to be at least that temperature. And things like that. I'm not someone who studies spectrometry, so I don't know all the details of how they do stuff. They even use spectroscopy to determine distances of very, very far objects. But I'm not about to get into that because that has a very long equation attached to it that I do not recall. But you can even use it to determine relative distances of objects. So, yeah. Woo! What else? What else is there? And honestly, that's how we determine. Anytime you see an astronomer on TV sitting there going, "Well, we've determined that there's a star 80,000 light years out there, and the star is mostly made up of carbon and oxygen and helium." That's how we know. That is exactly how we know what it's made out of and how hot it is, and all that good stuff. So, yeah. Did you guys know that we are 96% blind if you look at the entire spectrum of light? Okay, light is, what we see is only 4% of light, total amount of light that's generated. Light waves come in many spectrums. The lowest is radio waves. You have radio waves, then you have microwaves, then you have infrared rays, then you have the visual spectrum, which is what we see. Then you have ultraviolet rays, then you have X-rays, and then beyond that you have gamma rays, which are the highest form of energized waves. And we can only see the visual spectrum. And what is this? This is basically our light, light forms on many spectrums, and why can we only see the visual spectrum, or why do we see the visual spectrum instead of the infrared spectrum, or the ultraviolet spectrum, or even the X-ray spectrum? And the simple truth is, it's no coincidence. It's because our sun happens to be a yellow sun, which yellow is pretty much right smack dab in the middle of the visual spectrum. You have, it's like red, orange, yellow, green, blue, violet. That's the visual spectrum, and yellow is right smack dab in the middle, which is where our sun is. And so our sun emits the most, emits tons of visual spectrum light. And when we evolved on the planet, obviously, since that was the most common form of light around, that is the form of light we evolved to be able to see. Now, if we had had a blue sun or a giant sun, it would have been much more likely that we might have evolved to see ultraviolet rays. Or if we had had a tiny sun, a red dwarf is what they're called, we might have evolved to see infrared rays. But we're all emitting, everything pretty much emits all those rays at all the times. Technically, you're emitting radio waves, kind of. Mostly what you emit as a human, you're hot enough to emit infrared rays. Your TV remote uses infrared rays too. But basically, the hotter the object gets, the different types of rays it emits. Very cold emits radio waves. Then it gets microwaves, then infrared. Our bodies, that's what we generate. We generate infrared rays, which is why if you look at someone through thermal goggles or infrared goggles, they show up like a frickin' candle, because that's what our body radiates, is infrared. So if our body gets a little more hot, and when I say a little, I mean that relatively, it would start glowing red, because it would move into the visual spectrum, just like a piece of metal. When you look at a piece of metal, it doesn't glow. It doesn't glow. Well, it does glow. It just doesn't glow in terms that we call glowing. What it's doing is it's emitting light, but it's emitting light on a lower frequency than our eyes can see. It might be emitting radio waves or even, infrared rays or whatnot. But when you start to heat it up, it gets hotter, and the waves it's emitting become more energized. And eventually, when it heats up enough, it starts to emit waves in the visual spectrum, which is why it starts to glow red. It was always kind of glowing, but now it's gotten hot enough that it's emitting the light that we can see. So now it glows red. If you get it even hotter, then it starts to glow orange, and then yellow, and then white, and then it kind of melts. But if it didn't melt, it would go on to blue, and then violet, and then it would go out of our spectrum range and start emitting ultraviolet rays and then start killing us. And then X-rays and gamma rays, and we'd be dead. But now here's an interesting question. A very, very interesting question is, wait. Why doesn't it glow green? It glows red, and you said that the visual spectrum was red, orange, yellow, green, blue, violet. So why doesn't metal glow red, yellow, or red, orange, yellow, green, blue? It goes red, yellow, orange, white, blue. So why? Why is that? And the simple truth is because it is glowing green. It is, but our eyes are not that sensitive to green. Not really. The cones in our eyes see red, yellow, and blue. That's what our cones pick up. And every color you see is a mixture of red, yellow, and blue. Remember the primary colors? You remember those from school, don't you? And everything we see is, like I said, is a mix of that. And our eyes just aren't that sensitive to green. It's hard for our eyes to make green. And what happens is, when a metal rod hits that spectrum, it kind of overloads our brain, because our eyes have so much trouble picking up that spectrum color that our brain's just telling us that we're seeing white. Because it confuses the brain, it overloads it a little bit, and the brain's like, it's white. You sure? Because that's just white. Because I see the it's white. Okay, fine, whatever. Which is why we also have, same thing with stars. You have stars that, you have, red stars, orange stars, yellow stars, white stars, blue stars. Same thing. Those stars generally are really emitting light in the green spectrum, but our brains are telling us it's white. So, yeah. Now, you might ask, well, but I've seen things glow green before, like, when you burn, what is it, like magnesium or something? Yes, but that's different. I don't know why we can see that one and how that is different, but, and it's not like I'm saying that we can't see green. Obviously, I'm staring at green grass right now. We can see green. It's just that, we have more trouble seeing green than we do the other colors. Speed bumps! Did not see that coming. So yeah. I'm gonna go ahead and end this now because I've been talking forever and ever and ever. If you guys have more questions, by all means, I will. I enjoyed this, so I will attempt to answer them. Okay. So I will take care. Or you guys take care. You guys take care. I won't take care. You take care, and I will see you guys later. Adios.